Thank you for joining today's RadSite session for our winter webinar series. We will be starting in approximately 1 minute. Thank you for joining RadSite for the third session in our winter webinar series, Machine Learning and Artificial Intelligence, Hype, Myth, Reality, and how it will revolutionize the practice of quality diagnostic imaging. Today's presentation will be moderated by Garry Carneal, President and Advisory Board Chair of RadSite, and will be presented by Dr. Eliot Siegel, RadSite's Chief Technology Officer and Chair of the RadSite Standards Committee. Before we begin, I would like to go over a few housekeeping items. Today's presentation is being recorded, and an email will be sent this week to all individuals who registered containing a link to the recording. Second, to minimize noise and distraction, all attendees' phones are muted. However, if you have a question or a comment during the presentation, we encourage you to submit it using the chat box section on the lower right side of your webinar portal. Now, let me introduce our moderator, Garry Carneal. Mr. Carneal is a leading expert in healthcare and has a proven track record in helping trade associations, accreditation organizations, and other health-related businesses achieve their business and financial goals. During his career, Mr. Carneal has brought to market over 20 accreditation programs. Garry, I hand the presentation over to you at this time.
Thank you, Julie, and welcome everybody. I'm very excited about today's topic. I think all of us in healthcare often think about how machine learning, technology, artificial intelligence can improve the services we deliver or the accreditation programs we run or other activities related to healthcare. I've had the privilege of working at RadSite for the past 6 years, and I've really enjoyed learning about the imaging space and thinking through how we can improve the quality benchmarking process. So I hope today's webinar presentation by Dr. Siegel will kind of add to at least my knowledge base and hopefully yours. I've been very fortunate to work with Dr. Eliot Siegel over the past 5 years in the capacity of supporting RadSite. Currently, he is the Chief Technology Officer and serves as the Chair of the Standards Committee. And I must say, honestly, without him, RadSite would not have had the successes we've had in terms of developing our accreditation program. So it's really been great to work with him. He has a very distinguished background, as many of you know. Dr. Siegel currently is a professor and vice chair of research informatics at the University of Maryland School of Medicine and the Department of Diagnostic Radiology. He's an adjunct professor at the University of Maryland, Baltimore County for Computer Science. He's also an adjunct professor in biomedical engineering at College Park, University of Maryland. And he also currently serves as chief of radiology and nuclear medicine for the Veteran Affairs Maryland Healthcare System located in Baltimore. Among his various accomplishments, he worked with the VA Maryland Healthcare System to develop the first filmless healthcare enterprise in the United States, and is well known for his work to help us move to a digital format. He has written and published over 200 articles and book chapters about PACS and digital imaging, and has edited over 6 books on the topic, and certainly has presented over 1,000 times on many topics, including obviously today's topic. He has been named Researcher of the Year and has received multiple awards for innovation, including the Smithsonian Award, and was selected as runner-up to the Educator of the Year for diagnostic radiology. I could go on and on about his accomplishments, but perhaps the 2 things that impressed me the most about Dr. Siegel is first, his tennis game. I made the mistake of playing tennis with him when I first got to know him, and we're about the same age, and boy, did he whoop me. So that impressed me even more. And then the second thing is the stories of letting his Tesla drive him from Baltimore to the beach, particularly over the Chesapeake Bay Bridge, which I think he may talk about during his presentation, but that's certainly one step towards artificial intelligence. So, Dr. Siegel, without further ado, the floor is yours.
Thanks, Gary. Thanks for the great intro. I really appreciate it, and I hope this will be fun and interesting, and really very much appreciate everybody for subscribing to the webinar and listening in, and I'm really looking forward to comments and questions that you have too, and I'll try and answer as many as I can during the session, and then if there are any unanswered ones, then I'll try and follow up after the hour is over also. So what I'm going to be talking about today is something that's probably, or easily actually, the hottest topic in diagnostic radiology and becoming one of the hottest topics in medicine, but also a really super hot topic in all areas, whether it's industry, finance, or just the biology and other sciences in general, and that's machine learning and artificial intelligence. And I hear a lot of misinformation, and there's sort of a lot of hype and myth. I'd like to talk about sort of what is the reality of where we are currently, and then I'd also like to comment, particularly since we're doing this under the auspices of RadSite, I'd like to just end with a little bit of discussion on how machine intelligence and how machine learning and artificial intelligence might be able to have a significant impact on the way that we do quality diagnostic imaging, and even have some implications with regard to accreditation too. So let me try to advance the slides, which it's not doing. There we go. So I'd like to dedicate this presentation to a couple of the dozens of radiology residents and radiologists and other folks in diagnostic imaging who have written emails to me asking me about, what from an existential perspective is going to happen to radiology. It's not unusual that I am asked by the parents of, potential budding scientists who have an interest in going into radiology. And many of my radiology colleagues and other colleagues in medicine have asked me about whether or not the specialty of radiology is going to exist in the next few years. And I get letters from first-year radiology residents such as Zhao asking the question about, what is the future of radiologists? This is another example. This is from an Italian second-year resident in radiology who essentially asks the question of how will big data and artificial intelligence impact the radiology market, and she asks whether she should switch to interventional rather than diagnostic radiology to ensure a long career. And pretty much every time you pick up a magazine, whether it's in diagnostic radiology or medicine, or here you can see The Economist with a whole section that was dedicated to artificial intelligence, promise and peril, and more recently, the march of the machines. And particularly when these articles, including these in The Economist, talk about replacing jobs with artificial intelligence, interestingly, and I believe ironically, one of the first jobs that they suggest will be replaced are the jobs of the radiologists. I'd like to address that in a little bit more detail. And I guess hearing all this, the Obamacare architect, Ezekiel Emanuel, gave the keynote talk at the American College of Radiology in the year 2016. and also then subsequently published articles in both the New England Journal and the Journal of the American College of Radiology, talking about artificial intelligence as one of the three major threats to the future practice of radiology. And he actually went so far as to suggest that radiologists may be replaced by computers in the next 4 or 5 years. Jeffrey Hinton, who's a professor at the University of Toronto and one of the pioneers in machine learning, and particularly technology we'll talk about called deep learning, and who's now also a Google employee, went so far as to say that if you work as a radiologist, you're like Wile E. Coyote in the cartoon, and that you're already over the edge of the cliff, but you haven't looked down, and there's no ground underneath. And he went so far as to say that they should stop training radiologists now. And finally, a CEO of a well-funded and well-known Silicon Valley startup company that was claiming to be able to do image automated interpretation actually said something that, paraphrased, essentially was that he wanted, his goal about 3 years ago was to get rid of the wasted protoplasm, quote unquote, sitting in front of the workstation that's the radiologist, and replace it with a much better and reliable and consistent alternative. Well, that CEO is no longer the CEO of that particular startup company, and I think that as time has gone on, some of these startup companies are beginning to realize it's a little bit more of a challenge than they thought. And this isn't the first time that it's been suggested that machines could do much of the work that doctors can do. This is from an image in an advertisement in 1904 from the Watling Company that said if you put a penny into the machine, it would put new life into you. And what this vibratory doctor does and why the doctor doesn't have a shirt on isn't really clear. But clearly that in 1904, doctors were not replaced by the vibratory doctor. And of course, anyone who's seen the dozens of Hollywood movies associated with AI, knows that kind of in the Hollywood concept, as the machines get smarter, they start rebelling against humans, whether that's in HAL 2000, from 2001, A Space Odyssey, whether that's Ava from Ex Machina, or even the Terminator series. As time goes on, there seems to be a conflict between the humans and the computers. So let's talk a little bit as far as reality about what is and what isn't machine learning. And let's go over some of the basic terms in artificial intelligence. So as far as terminology, artificial intelligence is sort of a very broad category that encompasses anything that has a computer doing work that might have been done by quote unquote intelligent humans. And that's a really broad kind of breadbasket category. Within artificial intelligence, there's many ways to achieve that. And one well-known way is machine learning. We'll talk about what that means. And so one subset of machine learning is neural networks or autoencoders. And one subset of those neural networks, or one type, is something called deep learning, which uses many techniques, including convolutional neural networks. So we'll talk about how convolutional neural networks are a type of machine learning, which is one form of artificial intelligence. We'll talk a little bit about why everybody believes artificial intelligence has arrived all of a sudden, even though the technology's been around for over 70 years. So the person that actually coined the term artificial intelligence in 1956 complained that as soon as it works, nobody calls it artificial intelligence anymore, which is, I think, very interesting and prescient, actually, on his part. AI is basically an umbrella term for a broad set of methods and algorithms and technology that seem to make software, quote unquote, smart and human-like. But, really depends on what exactly the system is doing. So, for example, you can buy these calculators for $1 online, and yet the things that these calculators do are things that would have been considered human intelligence many years ago. And artificial intelligence, like these calculators, in the current state of the art in 2018 is incredibly narrow. And it's referred to as either narrow artificial intelligence or weak artificial intelligence. It specializes in one area. So you can go online and download a software program for free that'll run on practically any computer that could beat the world chess champion Magnus Carlsen at chess, but that same program couldn't beat a 5-year-old at tic-tac-toe because it's designed specifically for chess. And we have a lot of examples of narrow AI applications that are in their own right really impressive, like speech recognition or translation. Garry mentioned the self-driving cars, and even IBM's Jeopardy was a really narrow program, even though it was kind of marketed as being able to answer open domain questions and tackle pretty much any question, was really designed specifically and narrowly for Jeopardy. I was actually for a while part of that Jeopardy team with IBM looking into medical applications. And assistants such as Siri, Alexa, Cortana, Google Now are all examples of narrow artificial intelligence. The next level of artificial intelligence is known as strong artificial intelligence or human level AI. That's when the computer is as smart as a human across the board and can reason, plan, and solve problems, think abstractly. Creating artificial general intelligence is a much harder task than creating the narrow intelligence that we have, and we're nowhere near close to artificial general intelligence. If you talk to the folks who actually go to the artificial general intelligence conferences, which admittedly are a biased sample of enthusiasts, those enthusiasts, when asked when are we going to achieve artificial general intelligence, when the computer is comparable to humans as far as how we measure intelligence, about 42% predict that'll happen in the next 12 years by the year 2030, another 25% by the year 2050, another 20% by the year 2100, 2% say never. And increasingly, people are appreciating how difficult it is to achieve artificial general intelligence, which some people believe would be required to actually replace a radiologist with a computer. So let's go on to what is machine learning. I think a lot of lectures that I've heard sort of equate machine learning with a really quote unquote smart software program that kind of acts like a mini brain and learns in a way analogous to the way the brain learns. But actually, machine learning is really a class of advanced statistical techniques that use progressive iterative approaches to solving linear algebra equations, kind of like a self-correcting spreadsheet where you have the input on one side of the spreadsheet, the out on the other side, and you adjust all the cells in between so that the input creates the output. The vast majority of these machine learning techniques have been around for many decades. And so machine learning isn't really like a, worm's brain that's going to be soon like a cat's brain and then a dog and then a human. It really uses something that is a technology much more analogous to an iterative spreadsheet. Unfortunately, I think many people confuse the term machine learning for this sort of auto programming spreadsheet type of statistical technique for a smart mini brain that learns with more data. And although it does things that are smart like a calculator does, it really uses a completely different mechanism than the way we think of as intelligence. Machine learning is predominantly about recognizing trends from data and recognizing categories and then creating a model from those and making predictions using that model that was created. And there are thousands of variants of machine learning techniques. And you'll truly, if you look at the literature and things that are being done in the healthcare space and even in imaging, you'll see thousands of different machine learning techniques. Machine learning is different from data mining. Data mining focuses on discovery of unknown properties in data. Machine learning focuses more on prediction based on properties that are learned from a training data set. Leo Bremen suggests that maybe better than using the term machine learning, statistical learning might be a better term for it, actually. And so when we talk about machine learning, what we're really talking about doing is building a model that is used to be able to make predictions and solve complex problems. So one analogy about kind of building a machine to solve a complex problem might be the whole idea of scheduling, radiology residents for their 4-year schedules of which specialties they end up doing. So when I was first starting as a resident at the University of Maryland, and they saw that I had a computer science background, they gave me the task, which had taken the residents months to do, of creating the yearly schedule of rotations for the radiology residents. And it was incredibly complicated because the residents had to have a certain number of months at the end of the year in certain specialties, yet there were issues related to vacation times, issues related to availability of certain rotations, issues about what the residents had already had for their rotations, and issues about certain residents didn't want to work with other residents, or attendings didn't want to work with certain residents. So the scheduling was complex. What I ended up doing is, rather than creating a mathematical formula, and there were no scheduling programs at that point that existed that would do it automatically, I essentially just created a random schedule, and then created trillions of random schedules, and then had the computer check each one of those to see whether they worked. So in the end, it took it maybe 2 or 3 days, but it actually came up with a schedule looking at trillions of randomly generated ones that actually was close to meeting the criteria. And so that program was praised as being really intelligent and really smart and able to do in a couple days what it took a couple months for the residents to do in the past. But the program was incredibly dumb. In other words, it truly was just random. But it was an example of building a machine that does a lot of complex calculations, in this case, in a really dumb way, to come up with a really smart answer. And we've done similar types of things where we've built a simulation to determine what would be the impact of adding an additional CT scanner to a radiology department, or an additional technologist, or an additional digital X-ray unit. And so even though you buy a CT scanner that's twice as fast as the one that you are replacing it with, that doesn't mean that you're going to actually get twice as many patients. And so you have to model in waiting time and technologist time and registration. And so creating a model of the department, allowing us to ask those what-if questions, is another example of building a machine that allows us to solve a complex set of what otherwise would have been equations that we would have had to have created, but building the machine and then being able to make predictions. And the same thing could be said about building a machine to play poker, for example, and being able to not use a mathematical equation to determine the odds of drawing a particular hand, but just playing large numbers of those hands and then observing what the odds are of drawing certain hands in certain situations. So building a machine, like machine learning, can help us if we have enough computer power to be able to solve really complex problems. So one example of this might be this survey. And so this is a very stereotyped 5-question survey that we could give to 10,000 people. And the object of the 5 questions is to figure out, based on the answers to these 5 questions, whether the person answering the survey is male or female. So we could come up with some silly stereotypic questions, like we could ask them, what's your favorite color, pink or blue? Would you rather watch Dancing with the Stars or an NFL football game? Would you rather watch Star Wars tonight or The Notebook? And clearly, no one of these questions would allow us to make the determination of male versus female. But with the answers to all 5, how would we be able to make the prediction of male versus female, and how accurate would we be? And if you had to create a way to make the prediction based on the answers of 10,000 people, how would you do it? Well, one way to do it would be to just look at correlations, right? Which of the 5 answers correlates most strongly with male or female? Then you might get a little fancier and do a statistical regression formula that would allow you to weight each of those 5 formulas and to look at relationships between each of the questions. But what you could do also would be to utilize a machine learning technique. And so it may be that there are certain patterns and combinations. Let's say that taller women who are under 200 pounds that prefer blue over pink prefer NFL football, but only if they prefer Star Wars. Or maybe men who prefer pink and are over 200 pounds that prefer Dancing with the Stars, but only if they're shorter than 5'7". So the point here is that there may be insights and combinations in the data that would be difficult to discover with a regular statistical linear or curvilinear regression formula, but those patterns are patterns that you could observe in a machine learning algorithm and then be able to recognize those patterns and then weight those patterns. And so a machine learning approach to this type of survey will always do better than a statistical approach. Let's take something that has a little bit more to do with an image. Is this a beautiful pig or an ugly pig? We've got 119 pigs, and if you take a look at the ratio between their eyes and nose distance and their nose height to width ratio, let's say that essentially you could create a graph of the beautiful pigs in red and compare that to the non-beautiful pigs which weren't red. Could you draw a statistical line cutoff between the beautiful and not beautiful pigs? Well, anywhere where you draw a line, you're really going to have problems making that prediction. But we humans can sort of see that the data itself is emerging as kind of a heart shape. And so if we had enough observations of pigs and those ratios, just from the data alone, a machine learning algorithm would be able to derive the formula that I've got up here that turns out to be the formula for a heart shape. And so this is just an example of making observations where the data itself is turned into a formula. And once we have the formula, then if we have a pig candidate in the future that we've never met, we could predict what's the likelihood that that pig would be described as a beautiful pig or an ugly pig. So what we're talking about is taking data itself and translating it directly into a formula, which is really the gist of machine learning. One other example, more relevant to radiology, would be if you took a look at benign nodules in green versus malignant nodules in red. It's really difficult to draw any one line or even a curvilinear shape that would separate out the red malignant tumors from the green benign tumors. And so sure, as nodule size gets larger, you're more likely to have a malignant lesion. And sure, as the lesions are spiculated, they're more likely to be malignant, but there's an interaction between those, whereas as the nodule size starts to get larger, it becomes smoother. And so the relationship between nodule size and whether it's smooth or not really is much more complex. A regression line would have difficulty making that separation, but a machine learning neural network could learn the pattern and see whether or not it applies to future data sets. And so we can essentially specify much more complex patterns of relationships using machine learning than we can with traditional statistical techniques. And so why does this work? Well, this is an article from MIT published in 2016, where they suggested that this deep or cheap learning works well because most biologic systems, like lung nodule malignancy, for example, tends to follow a relatively simple formula and relatively simple equations, which is interesting. So overall, I believe that unlike what Hinton and Ezekiel Emanuel and others are suggesting, that medical imaging is likely to be the hardest specialty for AI software within medicine, and that many other specialties would be much more easily replaced. The other thing is that, the question is, what's the magic of deep learning as applied to image recognition? And we'll talk about that in just a minute. So this is a picture from Highlights magazine that you might recognize from a dental office, or that you might recognize from a doctor's office, or you might even have seen at home. And the object of the game is to ask a kid, what do they see that's wrong with this picture? So in this case, we see a TV on the roof, and we see a big fork and a spoon that's held by the farmer, and the dog's got a toothbrush. Well, if I told the computer and programmed it to find a TV or a spoon or a fork, that is a really easy task that computers now are able to do with incredible accuracy and rival a human. But the question of what's wrong with this picture, and then taking this picture or putting it in another context, is something that no supercomputer and no algorithm, for however many billions of dollars are invested, at this point, we have nothing that can beat a 5 or 6-year-old at that task. So the task of what's in this picture is fundamentally much easier for these algorithms than what's wrong with this picture. And we'll talk about the implications of that for diagnostic radiology. So in Scientific American, in June of 2011, they suggested that a better test for consciousness than the Turing test might be this test of what's wrong with this picture. You probably recall that the Turing test was proposed in 1950 by Dr. Turing, who said that once a computer is able to fool a human into thinking it's a computer or not being sure, that's when general artificial intelligence or consciousness will have arrived. Well, actually, it's been demonstrated that we have the technology to make it difficult for a human to tell whether something that is texting is actually a human or a computer. And so this test of what's wrong with this picture actually seems to be a much better test of artificial general intelligence. And that's something that is really well beyond our technology currently. So let's just talk for a couple minutes about what is a neural network. Well, a neural network has been described as modeling in a loose way the neurons that we have in the brain that are interconnected. Actually, the connections within the brain are far, far more complex than the connections in a computer neural network, which behaves much more like a spreadsheet, such as Excel, than it does the human brain, which acts much more like a quantum computer. But in this model, you have, just like a neuron, you've got inputs that are like dendrites, and then you've got the cell of the neuron itself, and then you have things that it ends up connecting to with other neurons. Inside a machine learning model, you have what you can visualize more as a spreadsheet, perhaps, than human neurons. And each one of those elements has certain weights, a multiplier, something that adds or subtracts, and then something that's called an activation function that is more of a sigmoid curve, or alternatively, it might be what's called a rectified linear unit, where you have something that has a 0 value until it reaches a certain point, and then it rises linearly. So through the combination in this quote-unquote spreadsheet type of concept for a neural network, we have cells that are interrelated to the cells on the left of them. You can have many layers of this very complex quote-unquote spreadsheet, and each cell has the ability to be able to be specified with a multiplier, an additive value, and then also this either sigmoid shape or this shape that essentially starts at a given point in a 0 until it reaches a certain point. And by putting all those together, you can do some really amazing things with machine learning in general, and in medical imaging, or just in imaging overall. It turns out that these neural networks, and specifically a subtype of neural network called the convolutional neural network, where the cells that are close to each other have a stronger influence than they do on cells that are farther away, those are very specifically optimized for human vision or image recognition or computer vision. So something really interesting happens when you connect these neural network algorithms to high-speed computers and pictures. So there was a challenge that was issued by Stanford called ImageNet. And they had images of cats and dogs and cars and motorcycles and other objects that were 240 by 240 pixels. That compares to a MR scan that's 512 by 512, or a CT scan that's 512 by 512, or an MR that might be a little smaller than that 512 by 512 typically. But even with this 240 by 240 pixel matrix, you've got about 58,000 variables. So if every pixel in an image of a picture, such as a human face or a cat or a dog, is assigned a variable, what happens as you get into increasing complexity of these neural net layers is you start seeing features. So you start seeing straight lines and curved lines and more complex features. And as you get deeper and deeper into the complexity of the levels of the neural network, it starts having the capability to distinguish complex objects, such as one face from another face. And you can use the same technology on scans, such as this MRI scan of the brain, where you have the image as an input, and then as an output, it can tell you whether or not that particular section of the scan has tumor or whether it represents normal brain. And this is similar technology that's to what has been used in recognizing a variety of different objects for the Stanford ImageNet challenge. So for all of us, including our residents that we're dedicating this talk to, Zhao and Andrea, if deep learning has been around since 1943, why is everybody so excited in the last 2 or 3 years? Well, a lot of that excitement has been generated by the hype and the true progress and true advances that have been done in human vision. Whereas in the year 2012, our colleague Geoffrey Hinton from University of Toronto was able to make a major jump from the error rate in recognition of objects that had been running around 25%. He got it all the way down to 16%, and subsequently now it's actually down below 3.5%. Last time it was done in 2015, and probably better. So it now is approaching human level performance. The problem is that even though these algorithms like supervision and others have approached human levels of performance, a lot of these folks who are experts in human vision have made the mistake of thinking, well, gee, if we can identify a dog versus a cat or a car or a motorcycle or other animals, we ought to be able to recognize medical images. But the problem in radiology is that the fundamental task is much more determining what's wrong with an image than it is recognizing objects in an image. And so it's a different task. So can we actually recognize specific things in a radiology image? Sure. Can we find lung nodules on a chest CT or a chest radiograph? Absolutely. Can we find microcalcifications on a mammogram? Yes. But each of those are very, very narrow tasks where you know what you're looking for. And like what we saw with Highlights magazine, if you tell it specifically to look for a large spoon or fork, then it has the capability of doing that narrow task. But in order to solve all the Highlights magazine problems, you'd have to literally have a list of tens of thousands of things narrowly to look for in every image, rather than a human, which would just be able to quickly say what's wrong with this image. And so that's one of the reasons radiology is so difficult. One of the things that we're seeing, though, is that the difficulty in creating a new algorithm is much lower than it used to be. So it used to take 3 to 5 years or more with many complex steps to create an algorithm to do something like lung nodule detection. Now you can create these algorithms directly from the data. And so the data itself, if we have, say, 1,000 or 10,000 or 100,000 chest radiographs, some of which have nodules and some of which don't, these machine learning convolutional neural networks are able to go directly from the images, knowing what the answer is, whether it's yes, there's a nodule, or no, there isn't, and literally adjusting this hypothetical spreadsheet that I'm talking about so that it's able to maximize the likelihood that it can recognize those. So instead of spending 2 or 3 years figuring out where the lungs are, describing what a nodule is, and going through all those steps, one can much more easily, with much less training and much fewer steps, turn the image data into algorithms that are able to perform a particular task. The problem is, even though it might be 10 or 100 times easier to train the algorithm with a data set directly, it doesn't take any less time to validate and make sure that what you have actually works. And that's a really critical distinction. So the other thing that's going to happen with these AI algorithms is because there are so many of them coming out, there needs to be a new model where we actually have something much more like an app store, where instead of going with one of the major vendors and getting all of their software, whether we use it or not, we'll be able to do what we do now. Instead of buying a record or a CD, we can actually get the apps that we want without essentially buying the whole album. And that's going to be very disruptive in the radiology space in a positive way. One of the challenges also is that it's really difficult to know how to test humans and human physicians to know whether they're competent at radiology. And the American Board of Radiology struggles with that constantly. How hard would it be to test a computer algorithm? What if we had Robbie, the rapid reading radiology robot from 300 years in the future that could interpret radiology studies, and we know that? How long would it take to test it on all anatomic areas and modalities and disease processes? How long would it take to get Robbie, the rapid reading radiology robot, through FDA clearance? Well, it might take 20 or 30 years, even if we had something that we were confident that could read as well as a radiologist. There are lots of other machine learning challenges. One is we don't know in any one data set which machine learning algorithm or what the parameters are to apply to that. And so another significant challenge is the black box nature of deep learning, where we may know that the data from the CT scans or MR scans or whatever we're training on is able to create an algorithm that can make predictions. We don't know exactly how or why it's making those predictions. And so it's hard to explain from a regulatory perspective, or even to someone who's going to use it, how it works and what it's doing. And so that makes it a lot less intuitive. And that's sort of the black box challenge. Another challenge is that some of these algorithms are fairly brittle in that you introduce a little bit of noise or change in the image, and it produces a major change in the outcome. So here we have an image that is classified as a panda with 60% confidence. We add a little noise. To our human eye, the image looks virtually identical, yet now the computer classifies it as a gibbon with 99% confidence. And so changes from one CT scanner to another can create significant issues. Also, we're still in a stage where it's even difficult for these computer algorithms to find the anatomy. I have gone around the world giving lectures saying that if anyone could write an algorithm that can find the adrenal glands on a CT scan, as well as a fifth grader, that I would wash their car anywhere. And so Brad Erickson and I, who've debated multiple times about how long it's going to take computers to replace radiologists, has declared that now I need to wash a car because a computer algorithm was able to achieve first about 68%, now 83% accuracy. But actually, and I can't show the video here, but I actually have a video of a fifth grader of a good friend of mine who spent about 10 minutes learning how to find the adrenal glands, and then case after case identifies exactly where they are and draws the outline. So I'm not actually ready to wash anybody's car yet until someone can actually beat my fifth grader here. There's nothing close now to general artificial intelligence to learn as efficiently as we train our residents. So one of the challenges that we have is getting the large number of thousands or millions of cases that might be required to annotate in order to be able to teach these machine learning algorithms. Machine learning techniques have been utilized for many decades, and we have literally, I would say, tens of thousands of very narrow algorithms currently that do something very specific. Combining them to essentially achieve what a radiologist can is something that we've not figured out logistically how to come anywhere close to. And one of the problems is, as time goes on, as the technology changes, we have to start from scratch and get a whole new data set as we move from 2D mammography to 3D mammography, for example, and as we get new techniques and challenges. And so it's very difficult and time consuming to annotate these images, and to a large extent, we've needed humans to be able to do that, which is super expensive. The National Lung Screening Trial Database, for example, took $250 million to collect, annotate, and be able to do all the logistics associated with it. Doing that for all of the different imaging modalities and types of studies would be extraordinarily expensive and time consuming. There have been some really interesting developments outside of medicine and radiology. And one of the most impressive teams has been the Google DeepMind team that was able to, for example, create software to play Atari video games by not teaching the computer or algorithm how to play each one of the games specifically, but to just have the computer watch the game, play it randomly, kind of like the radiology schedule that I made, and then learn by watching the score. And so it's really impressive to watch the algorithm, which only learned by trial and error, be able to learn, these 60 or 70 Atari games. You're probably familiar with the fact that the DeepMind team was able to master the game of Go and beat the world champions at Go, which people had predicted wouldn't happen for another 10 or 20 years or so. And the same thing has happened even more recently, where an even stronger version of AlphaGo, which is called AlphaGo Zero, beat the original version 100 games to nothing by just playing games using something called reinforcement learning without even using human games. And the same thing has happened even more recently by having Google's AlphaZero software destroy the best computer chess program after trial and error playing chess and discovering strategies in just a few hours. Garry mentioned a self-driving car, and this is me in my car crossing the Chesapeake Bay Bridge. And one question might be, well, even though, you might hear that the algorithm for self-driving is 5 times safer than a human driver, when it makes a mistake, it might make a really egregious mistake. And so how do you debug software that's just learning from data and observations? And could we trust a driverless car completely? And how would we debug it? And then how would we debug software that acts as a doctor or does medicine? There's also, of course, major regulatory and medical legal challenges. How would you get approval for self-reading software that claimed to read like a radiologist? What would be the medical legal issues? Who would take responsibility? The Harvard Business Review had a really interesting article suggesting that although computers are getting really good at making predictions, humans, particularly in medicine, I think, are going to be needed for a long time for their judgment. Could a Dr. Watson or could a computer program be empathetic and confident and humane, which is what most patients are looking for? And the answer is yes. There's some really interesting developments in having computers be able to demonstrate qualities that humans would associate with empathy. And so one other point that I'd like to make, particularly looking at image quality, is that although most of the attention and hype has been associated with computers making findings from the images, machine learning is going to revolutionize radiology even outside of the medical images themselves by allowing us to do some really interesting things that we haven't been able to do in the past along the ideas of efficiency, communication, and quality and safety. So one of the things that PACS systems typically get wrong is hanging protocols for radiologists, where they really don't do a good job, but yet watching as a radiologist themselves puts the images up, and learning from that and making predictions would, in my opinion, blow away the best systems that we have currently to try to have rules that the radiologists set a priori. Image optimization, protocol predictions, how do I make what protocol do I use? We've used machine learning for that at University of Maryland. Contrast enhancement quality, taking an image and having a machine learning algorithm grade the image according to quality of contrast enhancement and make suggestions for improving that, for contrast injection rates and amounts for the future for patients, image report quality review, CT and MR optimization, image noise and dose optimization, patient tracking over time. There are dozens and dozens of applications in image quality that machine learning should be able to do. And even within the realm of accreditation, what we would love to be able to do at RadSite is rethink and reinvent the accreditation process using systems such as artificial intelligence, deep learning, machine learning types of technologies to be able to not just every 3 years, but on an ongoing basis, assess image quality, assess quality of reports, quality of communication, quality of protocols, and be able to apply that. So I think next generation accreditation is going to heavily depend on automated information systems that constantly monitor quality and allow accreditation organizations such as RadSite to be able to review data that's already being collected automatically by folks that are doing imaging. And so there are many practical applications for machine learning and appropriateness criteria, protocol optimization that could all make radiology so much better and make the accreditation process not only more accurate and relevant, but actually make the accreditation process significantly less burdensome for those getting accredited. So getting back to Zhao and Andrea, radiologists do so much more than just making findings on medical images. We judge, explain, quality check, counsel, commiserate, teach, discover, lead, console, explore, create, innovate, and dozens of things that computers can't even begin to do. So in the future, Dr. Erickson and I, in our debate, believe that computers will perform many tasks performed by today's radiologists. Computers will perform much more quantitative imaging and assessment. Radiologists are much harder to replace than has been appreciated, and I actually believe we're going to need more radiologists in the future rather than fewer. And there are dozens of great applications in workflow, patient safety, communication, quality assessment, and others that these new emerging deep learning technologies will allow us to be able to focus on. So there's lots of low-hanging fruit for machine learning techniques that we should be pursuing much more aggressively. And I'm really interested in an ongoing dialogue about improving quality and also improving the entire process by which we do accreditation for radiology machines and practices. So thank you all so much for attending the webinar or listening in later. I really appreciate it. And any questions or comments, I'd be delighted to answer. So thanks. I'm going to turn it back to Julie.
Well, actually, this is Gary. Thank you, Dr. Siegel, for a great presentation. Very, very informative. And if anybody does want to ask a question, please use the chat box to send us a question, or a few have come in. So let me just jump right into it in the few minutes we have remaining. And I guess the first question is, with all, Dr. Siegel, with the kind of the disclaimers and caveats regarding where artificial intelligence can work, and for example, the distinction between machine learning and the potential for data mining, what actually keeps you up at night regarding AI? If it's if it's been since 1943 that all these developments have been taking place.
Yeah, so ironically, what keeps me up at night, or what I'm most concerned about, are number one, the fact that it's the perception that radiology is going to be replaced that I think is way more challenging than a lot of the things associated with applying artificial intelligence. For example, I'm doing a survey of medical students across the country and collected data from many medical students at many medical schools, and they're saying that they're being told not to go into radiology and that radiology is far less attractive because people have been reading that radiologists are going to be replaced by computers and the specialty will no longer exist. Well, the truth is that the specialty is going to thrive, and that radiologists will be the most difficult to replace, and that there's nothing in anyone's career horizon, as I would advise fellow radiologists who ask me about whether their kids should do radiology. So one thing that is concerning to me is the potential for not getting the best and brightest medical students because they're being told this incorrect information by so many different sources. Another thing that keeps me up at night a little bit is the potential for algorithms to be developed outside of radiology, outside of the FDA clearance process, and where people are told they can just send in their CDs, and an algorithm that is developed by some startup company that's not validated properly could end up giving them misinformation. And how one would regulate that. There are already over 100 algorithms for dermatology where people end up sending in their images, but you have no idea how the data set or how the machine learning algorithm was validated and whether it works or not. My concern is whether or not, now that patients have access to their images, where they might similarly send images out where they may be getting misinformation. So it's those sorts of things that really concern me as we're moving into an environment where these algorithms are becoming more ubiquitous and easier to create.
So kind of one related question is, it's fascinating, I don't know if this is part of the human condition, but when you have Ezekiel Emanuel and others predicting the demise of the traditional practice of radiology offset against, your observations, why do they draw that conclusion? I mean, is your perspective that unique? Is cognitive dissonance in play? What is going on to kind of downplay the role of radiologists when you see a factual presentation like this about the many years to come that we're going to need radiology as it exists today to continue?
Yeah, so I guess another way to phrase your question is, how could these experts in machine learning get it so incredibly wrong and make these incredibly brazen, bold predictions that are clearly incorrect? And so the answer is that you have to understand the domain. And I think the idea that we're able to have a computer vision program that can tell zoo animals apart as well as humans can, that you need to have expertise that crosses between computer science and medicine to appreciate the complexity and the limitations of computer science. If you're an expert in medicine and you don't understand computer technology, it's really hard to understand how these algorithms can be best utilized. If you're a machine learning expert and understand little or nothing about diagnostic imaging, you end up making predictions because you simplify the task. But as somebody that's been doing research in machine learning and artificial intelligence, reviewing papers over the last 25 years, I can see the incremental gains that we have. And, the science is getting better and better, but the rate of, new FDA clearance, the rate of these new algorithms coming out and being able to be validated has increased only slightly because of the bottlenecks in doing the annotation and in verifying these algorithms. And so because of that, even as somebody that develops them and is a proponent and also reviews the science associated with computer science, I feel that those of us in radiology with a computer science background are much better able to make that determination. But what's really important is that we make sure that we have people in medicine and in radiology who have enough of an understanding of the computer science so that we can maximally take advantage of all the really cool possibilities that the developments in the technology that have been applied to self-driving cars and translation and speech recognition, all those cool developments can be applied to make radiologists safer, more efficient, more effective, smarter, decrease the discrepancies in expertise of care in different areas of the country and different areas of the world.
Great. I think we have time for one more question. And actually, this comes from a RadSite committee member who's challenged you to a tennis match, Dr. Siegel. I'll let you know who it is after the call. But I know I have some knowledge that you may have met your match with the challenge.
I may have, and I just want to respond to that challenger that one of these days there's going to be a tennis playing a robot on the other side. It might take a while before that can replace human tennis players, but it'll be fascinating using these same human vision technologies to see what happens in sports with that too. So I'm really looking forward to the challenge, and I'm hoping I can get a lot of tennis in before I get replaced by a computer tennis player.
So I think you addressed part of their question, but the question is, how is RadSite going to continue incorporating, components of artificial intelligence and preceptor practices in its own accreditation activities. And I guess I will just add to that question in terms of it sounded like one of the opportunities is really to kind of take metrics and promote, quality and safety benchmarks. So as part of that, what could RadSite or another accreditation organization do? And then I think related to that is, who's going to pay for it? What will create the marketplace changes? And then also, how do you create a call to action so that all the applicable stakeholders modify? For example, if RadSite's able to kind of produce through measurements off the DICOM header a more real-time feedback loop, how do we actually change the practice of radiology to reflect, the recommendations coming in a more real-time basis instead of every 3 years during the accreditation recycle?
Right, so that's about 2.5 hours worth of questions, but let me try and give you a 30-second answer to that. I think what's going to happen is that we're going to have increasing regulatory requirements to up our games as far as demonstrating quality. And I think whether it's the American College of Radiology, whether it's CMS, whether it's other regulatory agencies, we're going to see the same thing in diagnostic imaging that we're seeing in other areas of medicine and surgery, and that is specific requirements for documentation of quality. And now that we've moved toward an electronic medical record and, of course, towards digital imaging systems, we're collecting an incredible amount of data. You mentioned the DICOM header information, and we're collecting all sorts of other data. There's little doubt in my mind from discussions with CMS, for example, that they are under increasing pressure and have increasing expectations for what is deemed to be quality, and also the process of collecting that information. So I think what's going to drive the investment is going to be increasing requirements that require data to be analyzed on a real-time basis as the only way to be able to meet the regulatory requirements. And in doing that, we need to take the data that we have already and have information systems that are able to process it. It doesn't have to be sophisticated, iterative machine learning technologies at first. It really is just a matter of analyzing and creating dashboards for the data that we have and reporting on it. As time goes on, though, making ourselves more efficient, smarter, and better is going to require using these more sophisticated techniques. So I think the answer to the question is that we're going to see in the very short term regulatory requirements that mandate our being able to analyze the data on a continuing basis. And I think we're going to get really smart about being able to do that. I think the current accreditation organizations such as RadSite are going to need to stay ahead of that curve and try to continue to be leaders with other folks who are leaders in radiology to help wisely manage those expectations from our regulatory friends.
Great. Thank you, Dr. Siegel. I know we're out of time. Before I turn it over to Julie to wrap up, if you, by chance, have any questions or comments regarding today's presentation, we'd be happy to follow up with you. Please send an email to info@radsitequality.com, info@radsitequality.com, and it will get directed to the right person. I think Dr. Siegel's offered to help write a blog summarizing some of the things that were covered today as well. So continue to monitor our website, which is www.radsitequality.com. And then just finally, from my perspective, if anybody wants to get involved with RadSite, we'd love to connect with you. We are a volunteer-based organization. Our committees are made up of volunteers, and we'd love to hear from you if you have any interests. And then finally, thank you so much, Dr. Siegel, for your presentation today. Really appreciate your time. Julie.
All right, we want to thank you all for attending today's webinar, and we hope that this discussion provided valuable insight into artificial intelligence in medical imaging. As Garry said, the recording of today's webinar will be available on our website by the end of the week, and we will be sending out an email with a link to that recording to you by the end of the week as well. And of course, in case you missed the first two webinars in the series, RadSite's Accreditation Overview and the importance of image physics testing, you can get those recordings by going to radsitequality.com and /webinars. The webinar page is located in the education session. As Garry also said, if you have any questions, please email them to info@radsitequality.com, and as we said, the appropriate person will respond. Again, we want to thank you for attending today's webinar and hope you have a great rest of the day.